The sizes for ions are going to follow the same basic trends as those for atoms, but there will be a few extra criteria. And using electron configurations can be pretty helpful. So we'll start with cations. Cations are always going to be smaller than their parent atoms, and the reason is you're removing electrons. So when you remove an electron, or more than one electrons, now there are fewer electron-electron repulsions, which would normally cause the electrons to be pushed further away from the nucleus. The lack of those repulsions, or the reduced number of those repulsions, means the electrons will be closer together and closer to the nucleus. The other thing that can happen is, now that you've removed an electron or more than one electron, the outermost electron might now be in a smaller n-value shell, which means it'll be closer to the nucleus. And we'll do an example with magnesium. So magnesium's electron configuration has its valence electrons in the 3s orbital. If you make a cation by removing a single electron, you end up with Mg+, which is unlikely to form, but bear with me because it's illustrative. With Mg+, you now have one fewer electrons than in magnesium, which means you have fewer electron-electron repulsions, and that means the electrons will be closer together, and they'll be closer to the nucleus. And if you make Mg2+, by removing an additional electron, you'll get this configuration. And now the outermost electron is in the n=2 shell, which is much, much smaller than the n=3 shell. And that means that magnesium 2+'s outermost electron is fairly close to the nucleus, which means the magnesium 2+ ion is much smaller than the magnesium atom. Anions are always going to be larger than their parent atoms, and the reason for this is almost exactly the same reason that cations are smaller. And we'll use the example of the chlorine atom and chlorine ion. Chlorine's valence electrons are in the n=3 shell, and if you add a single electron to make chlorine minus, the chloride ion, you'll get this configuration. You have one additional electron in the n=3 shell, and that means you have more electron-electron repulsions, so those electrons are going to be pushed further away from one another and further away from the nucleus, which makes the ion larger than the parent atom. There's also the possibility that if you add enough electrons, you might end up with the outermost electron being in a larger n-value shell, but this is extremely unlikely to happen, so I'm not even going to give an example of it. And now we should learn a new term, a new word. Isoelectronic simply means having the same number of electrons. So I want you to consider the following series of ions and atoms. Each one of these atoms and ions has exactly 10 electrons. So we can say that this series of atoms and ions is isoelectronic. And something interesting about an isoelectronic series, like this one, is that you can now rank these in order of size by comparing the effective nuclear charge. Each of these different species has a different number of protons, but when you write the electron configurations, you'll notice that all the electron configurations are exactly the same. And now we can work out effective nuclear charges for each of these species. There are 9 protons. There are only 2 inner shell electrons. At this point, the outermost electrons are in the n=2 shell, and the inner electrons are in the n=1 shell. So there's only 2 screening electrons. And that means that the Z effective, the effective nuclear charge for the fluoride ion, is 7. And we can see that the effective nuclear charge within an isoelectronic series gets bigger as more protons are added, which seems entirely reasonable. And because magnesium 2+ has the largest effective nuclear charge, and its electrons are in the same shells, same positions as all the others in this series, the magnesium 2+ is going to be the smallest. And by a similar argument, the fluoride ion has the smallest Z effective, so it will have the largest radius. And there's another term that we should learn that's very, very similar, and that term is valence isoelectronic. So every atom within a single group is going to be valence isoelectronic with all the other atoms in that group. So we'll look at the alkali metals as an example. In each of these cases, in each of these atoms, the valence shell contains a single s electron. That is, they have the exact same valence configuration. And this similarity between the valence shells within a group goes a long way towards explaining the properties and behavior of those atoms.